Hi, also today we are going to talk a little bit about order of reaction. I think, having had a look in the Google Classroom, that you might have already done a little bit of this with Miss Clark, so you might find this is a very straightforward lesson. So, order of reaction is a term that we use when we're talking about kinetics, and really it's what most of your A2 kinetics topic is based on. And it boils down to thinking about the effect of concentration on the rate of reaction. So at GCSE, and even in the last few lessons, I might have said to you that as the concentration increases, the rate of reaction increases. And the argument for that is collision theory. It's the fact that there are more particles in a given volume, and therefore there is more likely to be collisions. Therefore, there's more likely to be more successful collisions, and therefore the rate would increase. But it's not necessarily true. And the reason it's not necessarily true, or the reason why we can't always apply it, okay, is that the often chemical reactions are multiple stage. They have multiple steps, okay? So the problem is you normally have multi-step reactions, often just two steps, and that's what we'll focus on. But there are normally kind of multiple steps. So you could have an equation, something like A plus B. So chemical A plus chemical B makes C plus D, and that could be our overall equation. But actually, what's happening, and I'll just zoom out so I get a little bit more space. What's happening in reality is that there are two steps here. There's a step where A is becoming an intermediate, and is becoming C. And then you could have a second step where B is reacting with the intermediate to form D. So you can see overall, if you put these two together, the intermediate cancels out on both sides. Okay. And you're left with A plus B makes C plus D, the overall equation that we started with. So we've got these two steps, okay? And the reason that's important and why that makes a difference is all to do with the kind of relative rates of those steps. So actually, the overall equation at the top, that's got a rate, okay? But each of these steps make up part of that rate. So let's say the first step where A is just kind of decomposing to be an intermediate in C, that's particularly slow. Okay, that's a really slow step. And the step where the B plus the intermediate reacts to D, that's a fast step in terms of rate. So the first reaction is happening slowly, second reaction is happening much more quickly at a much faster rate. So why does that matter? Well, it means that actually, if I look at my equation here, and if I was to increase the concentration of B, let me just move that back down, sorry, let me move that a tiny bit, there you go. So if I was to increase the concentration of B, the concentration of B, what does that do? Well, it increases the rate of step 2. But step 2 was the fast rate anyway. And it really didn't make much difference to the overall amount of time, because actually if A is really slow, the majority of the time this reaction is taken to happen is happening in step 1, okay, where A is being decomposed. So actually the overall rate is going to be essentially unchanged, because that first step is so slow, it takes so long, that it is if you increase the speed of the faster step, the second step, it's really not making much difference to the overall time. And I think Jim Clark in the Maths for Chemists in the Jim Clark book, The Calculations, he talks about, he uses a travel analogy. So he says if you were to be travelling from Dorset to New York, okay, there's 2 steps to that journey. There's getting from Dorset to the airport, it might be getting up to Heathrow, and then there's flying across the Atlantic, okay. Now, if you were to say that the first step, you were walking to Heathrow. Now, walking to Heathrow is going to take you several days, most likely. So that is a really slow step. And then the flight would be a very fast step. So actually, anything I did to the flight, if I changed the flight from a 747 to a Concorde or a jet of some sort, a supersonic jet of some sort, then actually, yeah, that might reduce the journey across the Atlantic by a few hours. But overall, that's going to make very little difference in the amount of time it takes from the start of my journey to the end of my journey. It's still going to be several days because walking to Heathrow took several days. Whereas if I was to increase my speed as I get to Heathrow, so if I was to take a train instead of walking to Heathrow, then that might reduce what was several days down to a couple of hours, and then that flight, in addition, is going to make a much faster rate of reaction. So the key thing to kind of try and take away from this bit is that the rate of reaction does not necessarily increase when you change the concentration of any one reactant. Okay, so the rate of reaction does not increase necessarily when you change the rate of any one reactant. It might do if it was to do with if you were increasing the rate of A, for instance, if you're increasing the concentration of A, therefore you'd be increasing the rate in reaction 1, which is the slow reaction, and then the overall reaction would increase its rate, it'd be faster. But if you're talking about B, it's not going to have an effect because that's already, you're just trying to speed up what's already a fast step. I'm going to tell you a little bit more about that in a second. So how does this link to order of reaction then? So something you might have been talking about with Miss Clark a little bit. Okay, so order of reaction is kind of the idea of kind of giving a bit of structure to working out how these how different the concentration of different reactants affect the overall rate of an equation, and kind of giving a mathematical way to represent that. So let's just think about a kind of an imaginary reaction, okay? And that imaginary reaction is one with, again, A and B. So A plus B react to make the products. We're not going to worry about what the products are in this case. Okay. Now you can imagine that if the reactant is A, one of the reactants is A, we could link the idea that the rate is going to have, there's going to be some sort of relationship between rate and the concentration of A. Now, like we said a minute ago, we don't know, unless we can work out experimentally later, whether A is necessarily taking part in a slow step or a fast step. So it's really hard for us to say, this is this exact relationship. But what we tend to say is that rate has some sort of proportional relationship to A to the power of N. And that N up there is the order of the reaction with respect to A. So this is what we call the order. And it tends to be either a 0, so 0 order, first order, a 1, or second order, amazingly, which is a 2. Okay, so what do each of those numbers mean? Well, it's kind of useful, so I always kind of keep it as a little table for myself. So we've got the order, and then we can think about what effect that has. So if we are talking about the different orders, so we've got 0 order, we've got first order, and we've got second order. Okay, apologies for the terribly drawn table. Okay, so the first thing is, well, what's N for each of these? Well, I've just kind of said it, but 0, 1, and 2. And what do each of those things mean? So this is where we kind of have to think about the effect. Well, if you are someone who does maths, or you might know this from your GCSEs, then anything to the power of 0 is 1. So the concentration to the power of 0 equals 1. So if we're saying something, some relationship between the rate, so the rate is some sort of constant times by the concentration of a to the power of n. Well, if it's a to the power of 0, that a becomes 1, and therefore there is no effect on the rate, okay? Because you're saying a constant times by 1, that's still a constant, so 0 order has no effect on the rate. What about, and changing the concentration would have no effect on the rate. So if I double a to the power of 0, even if it's 2 times a to the power of 0, it's still 1, because to the power of 0 turns it into 1. If we're talking about first order, we're saying a to the power of 1. Well, the concentration of a to the power of 1 is just the concentration of a. So this is what we would say is almost directly proportional. It's proportional. Proportional. If I can fit that in there. So it's proportional to the power. And essentially that's because the rate is going to be related to a constant times by a, because a, the concentration of a to the power of 1 is just the concentration of a. Sorry, I say a and I mean the concentration of a sometimes when I'm talking. And finally, it means the second order, okay, you're talking about the rate is equal to a constant times by the concentration of a to the power of 2 or squared. So actually it's going to not be proportional. So this is proportional to a, concentration of a. This is going to be proportional to a squared. Okay, so what does that actually mean? Let's just take it down a little bit and see whether that we can make this a little bit more logical, make a little bit more sense. So, for instance, what would happen if I doubled the concentration of A? So what would happen to the rate of this reaction at the top, at the very top that we had a moment ago, if I doubled the concentration of A? Well, for instance, if A was 0 order, I've got 2 times A now, but it's to the power of 0, so A, 2 times A to the power of 0 equals 1. Okay, so I've got a constant times 1. So what happens to the rate? Nothing. The rate is unchanged. So the rate would be unchanged. Whereas, if I'm talking about something being first order, if I was to double the concentration of A, well, now this is 2A, and it's a constant times 2A rather than just times A, so actually my rate would double. So the rate is 2 times what it was previously. Okay. And finally, what about if my rate, if I've got a rate equation that is, or where the concentration is second order, so it's squared, well then 2 times A actually is essentially saying it's increased by 2 times A all squared. So you're squaring that 2 essentially, so the rate will be times 2 squared larger, which we could also say is times 4, because 2 squared is 4 times larger. Okay. It's really important that we can try and apply this. It will become a little bit more apparent with some questions, I think, and we'll probably have a look at some questions in a moment. Before we look at a couple of questions, though, I just want to think a little bit about the overall. So if we look at this all here, we've got the whole thing in shot. So the rate, with respect to A, is a concentration of A to the power of n. And we can't find out n unless we do it experimentally. We have to find it out experimentally. But there's kind of two ways we think about this. We've got the whole reaction, okay, there. So we need to think about the reaction rate So that's just the relate. What we've got here in a minute, let me just point at it. What we've got here in a minute is just the rate in respect to A. But if we're trying to think about the overall rate of this whole equation, the whole reaction, then we'd end up with a rate constant or a reaction rate that would look something like this. So you'd end up with the reaction rate is equal to, I'm going to write it down below just so you've got a bit of space, some constant, and we call that constant K, to the power of, times by A to the power of N, like we've said before, and B to the power of, well, we'll call it M because it doesn't have to be the same as A. In fact, it probably won't be the same as A. So I talked about N in the beginning, but actually N and M, it can be to the power of anything, okay? So you'd have your reaction is, the order of reaction in respect to A is N, the order of reaction in respect to B is M, and the overall order of reaction for these two is M plus N, or N plus M, whichever way around you do it, okay? So that's important, that there's a difference between the order of reaction with respect to a given reactant and the order of reaction, the overall order of reaction, which is the sum of the powers of the concentration terms in the rate equation. And this is up here, this part is what we call the rate equation. Rate equals a constant K times A to the power of N times concentration of B to the power of M. Okay, the rate constant, this K, will be different for every reaction, but it is a constant. Okay, so a constant is something that doesn't change. In some reactions, you might see a catalyst in the rate equation. The units of K depend on the order of reaction, and the only thing that affects K, changes K, the rate constant, to be a slightly different constant, would be temperature. So temperature could affect K, but otherwise nothing else affects K. So I'm going to write down a reaction, and we'll have a go at some questions together, and then I will leave you guys some problems to have a go at. Okay, so again, let's consider, we'll leave all that up the top, so maybe you can see it if you're looking very closely. Let's consider a reaction that's happening, and we're going to keep it again as a bit algebraic, a bit abstract, because I don't particularly want to go into a real life example so at the moment. So we've got A plus B plus C, and let's have it make D. Okay, and this is actually the first task I'm going to give you, so this is part of that first task. I'm going to do a couple with you, and then you guys are going to take over from there. Now the rate equation, for this I'm giving you the rate equation, so the rate equals K, the rate constant, times by the concentration of B times by the concentration of C squared. So actually, let's think about the order of reaction here. So A isn't featuring in the rate equation, so that means A must be, so the rate in relation to A must be 0 order. Why do I know that? Because A doesn't feature, so it means A, if you imagine A could be there, it'd be A to the power of 0, and that becomes 1. So K times 1 times B, the concentration of B times concentration of C squared. So that 1 can just disappear. B is there just as itself. It's just there as its own concentration of B. There's nothing there because it's to the power of 1. And if it's to the power of 1, that means it's first order. C is there squared, so C is second order. So we've got 1 of each here. Okay. So what the question is going to ask you to do, so going to give you the initial rate. So for example, the initial rate, let's say the initial rate is 2.5, and the units would be moles per decimeter cubed per second. Now, it's then going to give you a change. So, for instance, it says we're going to have 3 times the concentration of A in the first question. 3 times the concentration of A. What is the effect on the rate? Well, A does not feature in this rate equation. The concentration of A does not feature in this rate equation. So by changing A, have we had any effect on the rate? No. So there is none. There is no effect on the rate. So what's the new rate? Well, the new rate is 2.5. Pretty straightforward for that one. Okay. Let's think about it, a different one. So they change it ever so slightly. So they change the what we're looking at. They change the rate, the initial rate, and they say it's now 0.75, and they lay it out like a table, so you'll find it's probably quite easy to fill in as you go. And they say, okay, in the second example, we are doing 4 times the concentration of B. What effect would that have on the rate? Okay, so is B in the rate equation? Yes, it is. Is it to the power of anything? No, it's to the power of 1, so it's directly proportional. So if I increase B 4 times, remember K is constant and the C isn't changing. If I increase B, the concentration of B, by 4 times, then the rate is going to increase by 4 times. So the new initial rate, the new rate, is going to be 4 times 0.75. 4 times 0.75 is 3. Again, it would be moles per decimeters cubed per second, but I'm not going to write those out now. Let's have a look at an example for C then. So they change the initial rate each time just to keep it fresh. I think 12, and they're saying in this case they're just changing the initial concentration of C and making it 10 times greater. So we're increasing the value of C by 10 times. And then we're squaring that, because in the rate equation up here, C is squared. It's to second order, so it's to the power of 2. So what does that mean? Well, it means 10. We've got 10 squared times larger. 10 squared is 100. So it's 100 times larger. So we've got 100 times 12, which is 1,200. So there, I'm going to use those as my 3 examples for you. So there are a whole range of examples, loads and loads and loads. They start to get a bit more complicated. So they start to do things like, what about if you increase the concentration of A by 2 and the concentration of B by 2? What would happen? So you do exactly the same process we did here. You take the increase, like 10 times, you put it into the equation, you see what would happen. So if that was 10 times bigger, that was 10 squared times bigger, so the whole thing would be 100 times bigger. So if you had 2 things, so if this increased by 2, this increased by 2, well, you'd have 2 times bigger because of this, and then once you made it 2 times bigger, then handle C. Okay, so if C's increased by 2, 2 squared is 4. So you've got it 2 times bigger because of the B, and then a further 4 times larger again because of C. And it is quite complicated, and it can get complicated. But actually, if you try and break it down into small steps, hopefully you'll find it falls into place. It's fairly straightforward. So there's a whole load of examples of that, and I mean maybe 20 more examples of that I'd like to do, and I will post those in the Google Classroom. So next time I see you, we will talk about finding rate equations using initial rates data from experiments, because remember, like I say, to find these you'd have to do that. I think you possibly have done some of that with Miss Clark already, so maybe this stuff is a little bit newer, and the stuff that we'll do next lesson is something that you have talked a little bit about previously with Miss Clark, because she's been going through the rates required practical with you guys. So we'll see how we go. I'll give you some feedback on your last lesson with the tangents, and you'll get that once I've heard from a few more people from the quiz. So that'll come back to you guys in the next sort of week or so. Have a good half term, and let me know if you need any help.